I'm not sure.
Test.
Test. Test. It's working?
Yeah.
Okay. 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 Let's start by myself. Okay. Oh, you do that? Do you? Okay. Perfect. Good.
Okay, good afternoon, everyone. Welcome to this session on Whitebox cryptography. So we'll have two talks about Whitebox ECDSA, attacks and countermeasures. So I believe those will be works, follow-up works from the Whitebox, last edition of the Whitebox contest, and some team that partner to brought those papers. So the first paper and the first talk is from people from Siemens, GND, and BSI, and the talk will be given by Dominic Klein.
Okay, thanks. So yeah, this is joint work by Sven Bauer from Siemens AG, Hermann Drexler from GND Mobile Security, and colleagues of mine, Maximilian Gebhardt, Friederike Laus, and Johannes Mittmann. And we are with the German Federal Office for Information Security. Now, my colleagues and myself, we have cushy government jobs. So naturally, we are bored all day long. And so we decided, hey, why not participate in the Whitebox contest 2021 in the chess challenge? And that was some interesting and novel challenge. And we didn't manage to make first place, but Sven and Hermann actually made first place in the attackers category. And then after they revealed themselves, because it was anonymous participation, we did a post-mortem together, and this is basically how this talk came along. So the setting in this contest was there were designers and attackers, and the designers had to submit an implementation of ECDSA in C source code and had to somehow hide the private signing key inside the implementation. And then the attacker's task was to extract this private key somehow. And then there was some scoring system depending on well, how long the attackers required to extract the key, or if they couldn't, and the performance of the implementation. Okay, and now you're probably all familiar with ECDSA, but just to give a brief recap. So you have some input value that's your hash over your message to be signed, and then you compute the ECDSA signature, which is a pair of values R and S. And so what you do is basically the first 3 steps plus some check, and that is first you derive some random value k, some ephemeral key k, and then you use that ephemeral key to compute this value R by using a scalar multiplication on your elliptic curve base point. And then in the 3rd step, you compute this value S by some finite field arithmetic. So that's the setting, but unfortunately within the setting you have no true source of randomness. That's a problem, because you can't link to def-u random or something like that. I mean, you could try that, but it was forbidden by the rules, and even if you do so, you can easily patch that out by manipulating the C source code. And actually some challenges try to do that, but yeah, to no avail. So what you have to do essentially is you have to implement a deterministic random number generator. So you have to take this hash value h as an input to some function that seeds the DRNG, and then you arrive at the state of your DRNG and you derive your random value k. Because h, the input hash, is the only true source of randomness that you have available. And if you have a look at this 4th equation, S becomes inverse of k multiplied by RD plus H, that gives rise to an equation, namely that's the topmost equation here. And I will write a slightly different version for the ease of presentation, namely RD minus SK equals minus H. And note that within this equation, the only 2 unknowns are D, the private signing key, and this random value K. The other values are known. Now suppose you compute M signatures, and then you have M plus 1 unknowns, because you have M random values K, ephemeral keys, and you have in addition the signing key. Now, how to attack that? So the most straightforward way would probably to reverse engineer the C source code and then somehow extract the private key, because it has to be inside there somehow. But as I said, we have cushy government jobs, so we are lazy and we don't want to put too much effort in it. So what other methods are there to break these implementations? And there are 2 classes actually that we'll talk about here. One is to use collisions to target this ephemeral key K, and the other one is to induce faults and then exploit collisions. So an easy example for collision attacks is this Sony variant of ECDSA, where you simply fix the random value K and don't use a different random value for each signature generation. And then it's easy because you can just generate 2 signatures, obtain 2 equations with 2 unknowns, and then you simply solve these 2 equations. And in fact, 33 out of 97 designs were susceptible to this fault, even though I have to say some test submissions, apparent test submissions, are included in these numbers. And the most sophisticated way to exploit this is what we dubbed ephemeral key differential collisions. And so the idea there is to exploit some weakness in the implementation of the deterministic random number generator. So suppose some bit of k only depends on a very small part of h. So for example, imagine the case where the topmost bit of k is just taken as the topmost bit of h. And for the rest of k, you just take something different, like, I don't know, a keyed hash function or something from the input. That means that these 2 hash inputs only differ in a very small value delta. And so the generated ephemeral key k, the random k, only differs in a very small part. And you can describe that part by some variable. Let's call it t. And then the idea is to find 4 suitable input hash values where this occurs, where you can express these random values k with a difference with respect to this value t. And if you find such kind of inputs and the DRNG has this weakness, then you can simply solve for these variables. And for this challenge, 49 out of 97 submissions were susceptible to this fault. Okay, and there were other faults or collisions with respect to the ephemeral key that you could exploit. For example, sometimes designers submitted 2 challenges and they changed the private key, but they didn't change the deterministic random number generator. And then you could do some kind of cross challenge collision and use that. And then you could also break the private keys. Okay, and then the other class of attacks are collision fault attacks. So what's the fault model that I'm talking about here? So you have these 3 crucial steps in the ECDSA signature generation. First, deriving this random value k, then doing the scalar multiplication, and then computing this value s with your arithmetic in the field. So let's suppose that you have some intermediate value that occurs here in one of these computational steps. And let's dub this v. Then we distinguish 2 kinds of faults that we can induce. I'll call a value fault if we fault this value v to some error value e. And I'll call this a differential fault if we apply some additive error to that. So we fault v to some v plus e, where e is the error term. Note that in general, this is 2 different classes of faults because you get different equational systems. For some special cases, like for example d, they are the same, but in general they are not. And then the idea is to find 2 hash values for which you can generate the same fault value e. And the important point here is that you don't need to know the value of e. You just need to fault the implementation that you obtain for these 2 different hash values, the same error term e. And then you can solve these underlying equational systems. So let me show an example. So for a differential fault in R. So again, this is our signature generation algorithms. And let's suppose we are here in step 4, and this computation R times D is faulted. So here we fault R somehow in the implementation. Right, like this, like we fault R to some R plus E, so this term becomes R plus E times D plus H. And let's suppose we are somehow able to induce this fault. Then you obtain for a given hash, you obtain 2 equations. The utmost equation is, of course, just the regular signature generation where we don't induce a fault. And if we induce that differential fault, then there's some additional term here that occurs, E times D. Again, we don't know the value of this term, of this error term, but it's within this equation. And then the idea is, as I said, to find 2 different hash values, here where you obtain the same error value, where the same error value is somehow generated in the implementation. And then again, you have your unknowns, and you can easily solve the generated equational system. And for the challenge, 39 out of 97 implementations could be faulted by this attack. And it includes some other faults where you target intermediate values because it's from a black box kind of view difficult to distinguish where you induced the faults in the implementation. Okay. Now for some experimental results. So the setup was like this. So we, as I said, wanted to automate things as much as possible. In fact, during the challenge, especially Johannes got very skilled at looking at obfuscated C source code and manipulating variables all over. But in general, it's of course better if you can automate these faults. And what we did was compiled the C source code, didn't look at the C source code, and then looked at valid opcodes of instructions, of assembly instructions, and just knocked them out. So kind of like skipping these instructions. So then that generates static faults, right? You compile the binary and then you execute the binary, but what you don't do is you manipulate the program execution flow. So you don't start the program and then during execution induce faults. You could also do that, but you require more sophisticated tooling or a manual approach. And then what we did was use a few fixed input hash values and generate a small number of generated signatures and just tried whether one of these faults occurred, collision faults occurred, or key collisions occurred. And in fact, all designs could be broken by faults or key collisions. And I think the winning challenge survived for only 33 hours, unfortunately. So I think we can say that this round goes to the attackers. Okay, here's some statistics. So for the key collision attacks, as I mentioned, the first two are this PlayStation 3 kind of approach, and the ephemeral key differential collisions, I've showed them. And here for the differential and value fault attacks, these are the stats, and I've included here a simple known fault, uncontrolled fault in R, which is not technically a value or differential fault, but it's also quite successful. One point that I should mention here, that for example this differential fault in the inverse of K only applied here to no challenge, but that includes, as I said, only static faults. If you manipulate the C source code, or if you manipulate the program during execution flow, then you could obtain many more faults and also such kind of faults. But again, this is a manual approach, at least with our current tooling. We also proposed some countermeasures. These are, I have to say, a little bit ad hoc, but they only target basically this fault scenario, this fault model that we are in. And there is a countermeasure dubbed infective computation that is motivated, I think, by this uncontrolled fault in R setting. And the idea is to represent sensitive values by additive shares. And that works for this simple fault attack, uncontrolled fault in R. Unfortunately, it does not work for these differential fault attacks, because if you represent values as additive shares and you have this differential fault, which is also kind of additive, that translates back to the original variable. And what we propose is actually combining this with some kind of multiplicative blinding. And that helps against these faults that I described, but of course, you could argue that there are many more attacks in the setting that are possible. And you could also argue that multiple fault attacks are possible, where you target two different memory locations and are able to force that to some specific value. Okay, to conclude, so various computational and fault attacks apply to Whitebox crypto, especially in this asymmetric Whitebox crypto setting. It was very interesting, I think, because that's, I think, a very novel idea to use Whitebox crypto on asymmetric cryptography. However, all challenges were broken by automated static faults or key collisions, and in particular these uncontrollable fault in R, but also the ephemeral key differential collision. And I think what is interesting there is that the value and differential faults, they are kind of novel, and I think those implementers didn't necessarily have them on the radar, but this uncontrollable fault in R is, I think, widely known in the smart card world, at least. And nevertheless, designers were not able to protect the implementation against that, because in practice, it's just different to predict, for example, what a compiler does, or how this code executes precisely. Okay, that's all. Thanks very much.
Thank you, Dominique. Any question? Yes.
There was a few things which you did not really specify here, like, for example, the choice of the elliptic curve, which could have an impact on the attack. And there could be some questions about obfuscating the elliptic curve, or even obfuscating the public key. For example, you could shorten the signature and have a slow verification. So there should be some additional obfuscation here. And the interesting question, for example, is there any impact of the choice of elliptic curve? And could the choice of elliptic curve be also obfuscated in this sort of implementation?
Yeah, so in this setting, the curve was fixed. So we didn't particularly analyze that. But of course, a lot of faults could be induced in some kind of computational step. For example, you could manipulate the base point of the curve, and then you obtain faults because that translates all in the scalar multiplication. So I think the choice of the elliptic curve certainly could make an impact, but we didn't investigate in this setting.
Any other question? Let me check the Zoom. Okay, one question from the Zoom. So, did you experiment with obfuscation which passed the automated attacks?
Sorry?
So the question is, did you experiment with obfuscation which pass the automated attacks?
Well, as I said, we proposed these countermeasures, but on top of that, we did not encounter obfuscation methods, known obfuscation methods which particularly protect against these known attacks.
Maybe the question is, could you validate with the proposed countermeasures that the automated attacks failed?
Well, in our setting, they failed, yeah, of course, but one problem that you always have, a lot of designers actually implemented their code and then used some automatic obfuscation tools on top of the code, and these are black box. You don't know what they actually do, and so we couldn't verify what impact such kind of tools actually have on the countermeasures. But in our setting, actually, it protected against these faults. Unfortunately, we also participated in the design category, and we didn't manage to protect against all faults during the computation.
Mm. Any other question? Maybe I have one question. Given what you've learned from this work, would you bet that for our next edition on ECDSA, we could see some implementation resisting a bit longer, more than 48 hours, basically? Yeah,
so I think it's possible, and I think we will also have an interesting follow-up talk about designing an implementation. I think from my perspective, one crucial point was that you had to submit C source code, and that's understandable because you want to make it all manageable for the attackers. But for binary code, for example, it's very difficult then to implement without binary code to implement self checks, for example, self code checks, where you verify that your code has not been tampered with and obfuscate that. A typical measure that you know from malware that is protecting itself or encrypting itself. And you couldn't do that here. So I think this is something that played part in the attackers category. So the attackers maybe had it a little bit easier because they didn't have to go into reverse engineering, or at least could attack completely black box. Yeah.
Yes, right. Okay. So let's thank Dominic again.
Thanks.
So the next talk is still about Whitebox ECDSA implementations, some attacks and designs, still from some team of the Whitebox contest 2021. And so different teams from Kozik, Eindhoven, IBM, IDEA, Labo. And the talk will be given by Agathe and sorry, I don't have his name. Okay, thank you.
Okay, so hello everyone, and thank you for the introduction. So as you may have noticed now, this presentation is on the same subject than the previous one. So sorry for that. Some of the slides are going to be very similar, but we're going to try to not spend too much time on things that were said beforehand. So contrary to black box and gray box attackers who only have a very limited knowledge of the implementation, a white box attacker is supposed to have a total access to the binary, so he can read and modify it at will. And in that case, the implementation itself is the only line of defense against key extraction. So scientific literature about asymmetric white boxes is scarce, and CHESS 2021 Whitebox contest was held in order to encourage practical research, inviting designers to submit ECDSA white boxes and attackers to try to break the corresponding submissions. So designers gained a number of strawberries, depending on their challenge performances and on the time that it took the attacker to break it, while attackers received a number of bananas that was equal to the number of strawberries of the challenge at the time of the break. And at the end of the contest, the winners were the designers of the challenge with the highest number of strawberries and the attackers who broke it first. So this paper is the joint work of two teams, Zero Key, who posted the two winning challenges, and the Real Idefix, who ranked third in the attackers podium and was the team who broke the most challenges. So in the paper, we describe both the implementations of Zero Key and the attacks of the Real Idefix, and we provide detailed information on which attacks succeeded or failed on each candidate. But before talking about attacks and countermeasures, let me remind you the ECDSA algorithm. Again, I'm sorry, but we don't have exactly the same notations. So first, a nonce K is drawn at random, and the points are on a given elliptic curve is derived from it. The first part of the signature is the x coordinate of that point. We call it little r. And the second part of the signature is the value s equals k minus 1 times e plus rd, with d being the secret key and e being the hash of the message. So notice that in that scheme, the sensitive values are not only the key d, but also the nonce k, since its knowledge allows the recovery of d from s. Furthermore, it is important that the nonce value changes at its execution of the algorithm. So it is very important that it is generated at random. But as it was said before, the lack of reliable sources of randomness is precisely one of the major issues of whitebox cryptography. And this is why in the whitebox model, the deterministic variant of ECDSA, where the hash is computed as, the nonce is computed as a function of the hash, is usually preferred. So now that we all have ECDSA in mind, we can start talking about the attacks that we use to break the various candidates. So the first idea that comes to mind when one wants to break a white box is probably to check if some sensitive values are manipulated in the clear at some point. And the contest rules clearly suggested the designers to use the GMP library for big number operations. So we decided to try to hook the calls to GMP functions using the LD preload trick that allows loading a specific shell library before all others. So we built a shell library defining the exact same function as the GMP library. Each of these functions simply updating a log of the given parameters before calling the real function. And we managed that our custom function are used in place of the real GMP ones. And then we only had to analyze the log to search for sensitive values such as D, K, RD, E plus RD, or things like that. Another solution to break any ECDSA white boxes is to exploit the biases in the nonce generation. So as we said before, the nonce is usually a function of the hash in the white box model. So if that function is not carefully selected, there could be collisions. These collisions can be very easily detected by just looking at the first part of the signature, and they lead to an easy key recovery. The attacker only has to solve a system of two equations with two unknowns in order to recover both the nonce and the secret key. And when we did not find any collisions, we looked for smaller biases in the nonce, and so we used well-known lattice-based attacks that allow one to recover the secret key of an ECDSA implementation from only the knowledge of a few bits of K for several signatures. And when the nonce was generated carefully, there still exist other attack paths that are inherited from the gray box model. So first, the side channel attacks can be very well applied to the white box model, but they were quite difficult to use in our context because of the size of the traces that could easily reach several gigabytes. So this explains why we did not really use this attack during the contest. Fault injections, on the other hand, proved to be very efficient in the white box model, where the attacker can directly modify the binary or use debugging tools. And there already exist attacks against classical version of ECDSA, but the deterministic version is far more vulnerable, as we saw in the last presentation. So here is, again, an example of an attack that can be performed in the white box model. So first, the attacker can compute a valid signature of a given hash value E. Then he can execute the algorithm on the same hash value again, but this time inducing a fault anywhere during the scalar multiplication. Since the nonce only depends on the hash value, its value remains unchanged, but a faulty value R prime will be used instead of R in the computation of the second part of the signature, yielding S prime equals K minus 1 times E plus R prime D. And the secret key can then be recovered from the valid and the faulty signatures, as is shown on the slide. So here notice that the faulty value, so here R prime, must be known in order to recover the secret key. But the interesting thing with this attack is that if the implementation is not protected, R prime is simply returned as the first part of the faulty signature. So it's going to be possible to disturb other variables than R, as we saw in the last presentation, but it's going to be a little bit more difficult since the faulty value is not just given for free. And to conclude this part, I would like to show you the results of our attacks. So the fault injections were the most efficient ones, with about 78% of the challenges broken. The exploitation of biases in the nonce generation also gave good results, with a score of about 74%. And hooking only allowed us to break the weakest challenges, but it's still interesting to see that it represents about 1/3 of the candidates. And with that, sorry.
So now we will talk
Okay, thank you. So the first idea is to apply the implicit framework for whitebox implementation, which is a novel encoding method first proposed for the whitebox implementation of symmetric primitives. So, but we agreed we want to secure more stories, so we introduce techniques from multivariate public crypto to add countermeasures against possible attacks. So finally, to comply with the rules of the context, we use the C obfuscator categories to obfuscate the source code. So the first technique, it's implicit framework, which is based on the concept of implicit function and implicit evaluation. So the idea is simple. Like if we have a function f with input x and output y, we have this equality. Then if we can find the function t of x and y, if we can show that these two equalities are equivalent, then we say this function t is an implicit function of f. For instance, t can be f of x minus y. So to evaluate fa, we can first substituting x equals a and then solve this equation tay equals 0. Here y is unknown. So definitely we want this equation solving be efficient. So we introduce the idea of quasi-linear implicit function, or QIF for short. So the idea is that for any given or fixed x, we always have this function t xy in variable y is a fine mapping. So this enables us to solve y efficiently by techniques like Gaussian elimination. So the implicit implementation based on two techniques. The first idea, so for a function f, here we write it in a round-based way. So that means we have f round functions. So the first idea is very commonly seen in implementation of whitebox symmetric crypto. We have this encodings of the round functions. So for any round function, we have one mapping before it and one mapping after it. The idea is that this for any bi and ai plus 1, they should be canceled out. And then this a1 and bt are external encodings. So in our implementation, we basically use fine mappings. And the second idea is that because we want to have to use these implicit functions, so here is like if we have a QIF for a round function fi, then we can easily transform this to a round function of encoded implementation of this round function. So basically, by combining these two ideas, we have an implicit implementation of any function f. So here is the to be more precise. Here is the pseudocode for our winning challenges. Here are two lines of code are very important. Here, this code in right actually give an implicit evaluation of the scalar multiplication kg. So here, this scalar multiplication is implemented in a round-based way, thanks to the idea of Montgomery ladder. So because here we are in the right steps, we mainly compute the modular p, but here in this right steps, we need to compute the modular n. So here, because p is larger than n in our case, so we need to deal with possible overflows. So we idea is to pre-compute at least R of possible conditions. So then we can deal with this. And more technical details, you can see our paper. So now we want to have more protection against possible attacks to win this context. So we use two tricks from the multivariate public key crypto. So the first idea is to add more obfuscation by multiplying random polynomials. So here, remember that we need to solve this TAY equals 0 function to implicitly evaluate this Y. So here, if we multiply a function, a polynomial of x, if we substitute a to x, so because this is a polynomial, so with high probability, this R of A will be non-zero. So we can divide it, and then we can still get the same equation. So this means implicit evaluation can be preserved with high probability. But to avoid the extreme case, we set an initial value to prevent failures. So the second idea is to have a masking for longs to avoid the bias of the most significant part of the longs key. So then by combining the implicit implementation and multiplying random polynomial tricks, we have the first challenge, Kane Ptolemy. So this challenge is supposed to be lightweight, to be compact and fast. And indeed, it's actually the most efficient design, and we get the highest number of strawberries. And then the second challenge is we want it to be more resistant against attacks. So here we add the masking scheme. Yeah, indeed, it's however the longest among all submissions, and it gets the second highest number of strawberries. We can say from these parameters, actually, it's net overhead compared with previous challenge, net overhead by a factor 4. So these numbers actually increase by a factor of 4. Now about regarding this security, actually our first network design can be easily break by our co-workers, but because our actual masking schemes, our second challenge is secure against automated attacks. However, it's as you know from previous presentation, our second challenge was broken by a fault attack. So the idea is simply to remove only one line of code for this challenge, and this will induce an uncontrolled fault in R, the first part of the signature. So this basically defeats the verification steps. Yeah. So to sum up, we present automated attacks breaking a large number of challenges, and it turns out fault attacks are the most efficient and effective technique. And we apply implicit implementation framework to ECDSA for the first time. And we have the best implementation, but broken by fault attacks. So to conclude, securing Whitebox ECDSA is still an open problem. So thank you for your attention.
Thank you for the talk. Very nice t-shirts, by the way.
Thanks.
Yeah, you can go. Yeah.
Thank you.
Any question?
Thank you for the presentation. Could you elaborate more about how the signature verification is bypassed by this uncontrollable fault?
Okay, I guess that's a question for me. Yes. Yeah. So here the idea is that I don't have much time to give details. So as I can say from their paper, yes, the technique is simple. Just remove one line of code. So it kind of they force our program to kind of skip these verification steps. And I think for more details, you may ask the authors. They are here. Yes, I should say this kind of surprising to us, yeah, because it's so simple and so effective. Yeah. Okay.
So thank you for the presentation. I just wanted to come back to what you said, because you said there were verification steps. Were you verifying that the signature was valid, or were you doing
here.
some recomputation?
Yeah, basically here, yeah. Yeah. So basically the idea is that if we have this, if some fault injected may cause some problems here, and then they may fail to pass this step, then in this way we can prevent fraud attacks. But the idea is clever, like you just bypass this step. Yeah. Yeah.
Any other question? Okay, there is one from the Zoom chat. So is it meaningful to apply hardware implementation into Whitebox cryptography for acceleration? So is it meaningful to apply hardware implementation into Whitebox cryptography for acceleration? That's pretty open question.
Yeah, that's an interesting research question, I think. Yeah, we don't discuss this in our work. Yeah, I think this can be something like for a second edition of this context. Yeah.
Okay.
Well, yeah,
Yeah.
just to add that the point of Whitebox cryptography is first to try to secure fully in software. So maybe we can use a bit of hardware, but the idea of like performing the whole ECDSA operations on hardware is not exactly what we want to do. But maybe there is a trick to, I mean, if you have secure hardware, why to do Whitebox implementations? The question can be asked. But
Yeah, I think maybe you might not have secure hardware, but if it's too slow or expensive in terms of computation, it might make sense to accelerate the hardware. Maybe that was
maybe.
Yeah, sure.
Yeah, since you talk about it, I'd like to ask the same question as for Dominique. What would be your guess for next edition? You think you could manage to build ECDSA implementation lasting a bit longer?
Do you want me to answer? I just think that maybe the problem with this edition was that the restrictions were maybe too tight. So maybe if we can use more memory or more time for the execution, it will be easier to at least build Whitebox ECDSA that are not broken by automated attacks.
Yeah, it probably makes sense. Yeah,
Yeah, I agree.
yeah. Any other question?
I was just wondering if all the attacks you exploited actually are a consequence of the lack of a true random generator, and so the fact that you have to use a deterministic ones, or if among the attacks you presented, there are some attacks that could apply in case of, for example, hardware implementations, not Whitebox.
I didn't get everything, I'm sorry, but you asked if some of our attacks also work on hardware implementations of ECDSA, something like this?
Yeah, if there are
With
some
true
attacks.
random generation?
Yes, if among the attacks you presented, there are some more general attacks that applies outside Whitebox.
Yeah, sure. Like the collision attack, for example, and the lattice-based attack can be applied on any implementation of ECDSA. It just depends on how you generate the nonce. And then for the fault attacks, you have some attack that can be performed on non-Whitebox implementations, but they are going to be maybe quite different and a bit more difficult to exploit because usually it's not deterministic versions of ECDSA. And some of the faults that we exploit need the ECDSA to be deterministic. So,
thank you.
So we're a bit over time, so I guess we should go for coffee break and poster session. Let's thank Agathe and Chaoyun again.
thank you.